everyone. Today I am going to start presenting the speakers, and it's a pleasure to be here speaking at this conference and presenting some researchers that are really important to this work. And firstly, I represent Miriam Manuel from University of São Paulo, who is going to speak on involutions at the crossroads of singularities and dynamics.
Good morning, and many thanks to the organizers of this great meeting. Thank you, Douglas and Ricardo and all the group for being so helpful and kind. I'm honored to be here to celebrate the birthday and the contributions of Marco Antonio Teixeira. This talk holds a special meaning for me because it reflects the collaborations we had. It's an opportunity, a great opportunity to collaborate with Marco Antonio and Solange Vassili as well, who is also here. So many thanks for that. So feliz aniversario, Marco Antonio. This is the title again, so Evolutions at the Crossroads of Singularities and Dynamics. The overview. So I'd like to read this text. This is actually the abstract that I sent to the conference. So an evolution is a map that is on inverse. This intriguing condition leads us naturally into singularities as symmetries of folds and into discrete or homogeneous dynamical systems as antisymmetries or reversing symmetries of reversible diffeomorphisms or vector fields. Around 20 years ago, Marco Teixeira introduced us to an inspiring path in these directions. And in this talk, I will present the developments in both directions we've made since then. So this journey has been undertaken in collaboration with Solange, with Marco, and also Patrícia Battistelli, Isabella Doriot, and more recently with Marcelo Salazar. So I start, I'm not sure if this is working, yes it is. I start with definitions, so evolutions again. A germ of diffeomorphism phi, so I will use the language of germs, is an evolution on Rn, 0, if f composed with phi composed with phi is identity. A fold, a map germ f is a fold if it's A equivalent to f0. This is called the canonical fold. So when we have this equality, we say that evolution is associated with evolved or vice versa. The singular set of f is equal to the fixed point submanifold of T. And here is an example of those. If we replace sign by the zero function, we have the canonical ones. And if we want a class of examples, we can just replace the sine function by any odd function. So divergent diagram, speaking by itself. In my case, I will talk about folds. So we have S folds in a divergent diagram. And for each fold, we associate these evolutions. So we have the S tuples of evolutions associated with a divergent diagrams of S folds. And one question is how the classifications of these two objects are related. So they are pretty much related. So to speak about classification, I will briefly define the equivalences in these two settings. So in evolutions, two S tuples of evolutions are equivalent if the corresponding involutions in the I position of each S tuple, if they are conjugate by the same age for all I. For diagrams, they are equivalent if the corresponding elements are A-equivalent, where we have the same diffeomorphism age on the source for any I. So the classification of divergent diagrams of folds can be reduced to the classification of the associated sequences of involutions. So here is the theorem. Two divergent diagrams of S folds are equivalent if and only if the S tuples of associated involutions are equivalent. Now, in this reduction process, a very important invariant appears, which is the trace of, the trace of what? We get the orbital representative, take the composition of the S involutions, linearize them, and get the trace of this linearization. So here I will talk about pairs of involutions, so S equals 2, and we consider transversality. Two involutions, phi1 and phi2, are transversal if the fixed point manifolds are in general position. That is, if the whole space Rn is the sum of their tangent spaces. For the abelian case, and the planar case on R2, if we have two involutions, transversal and commute, then the pair is equivalent to the canonical pair. If they are not. If they do not generate an abelian group, for the planar case, the classification depends on these two spaces, the fixed point sets and the antipodal of a fixed point, that the antipodal of an involution, for the case that this is defined for linear involutions, this is the set of x, such that phi of x equals minus x. So when these two sets are equal, then the pair is equivalent to this, and otherwise, this is equivalent to that. So this picture shows the diagram, the bifurcation space, showing that we have a two-parameter problem. So each orbit is either a hyperbola or the A12 axis, the horizontal axis, minus 1 point, and 1 point itself. This point represents the pairs that generate abelian groups. For this normal form, we have these elements represented on here, and then here I pick one orbit representative to produce this normal form. And for the others, we have this thick line, and this is parametrized by the trace of the composition. And we choose 1 point to reproduce the normal form. So here we can observe that generically, so for all these cases of the hyperbolas, the trace is not only an invariant, but it's a complete invariant. Okay? It characterizes the orbit. So this is a consequence that's here in this corollary. So for the planar case, we know that the trace characterizes composition. So generically, two linear involutions are equivalent if and only if the compositions are conjugate. So what about higher dimensions? So the results for on R2 generalize for higher dimensions, and an interesting bifurcation phenomenon occurs when the dimension increases, and as follows. We can follow this path to reach 4 orbit types, depending now before for the planar case was equality of these spaces, and now are inclusions or not. The next slide I reproduce the normal forms. So for each of the 4 cases, non-abelian, these are the normal of evolutions in symmetric dynamics, motivated by the idea of how formally hyperbolic, so a germ of isomorphism F is normally hyperbolic if the fixed point set is a submanifold and the spectrum of the derivative at 0 has n minus k elements out of the circle S1, see, where k is the dimension of this submanifold. In particular, when k is 0, this is hyperbolic case. So we consider L a linear normally hyperbolic isomorphism, decompose the whole space as a direct sum of the stable, unstable, and the fixed point spaces of L, and we consider this hyperbolic bundle of automorphisms over the identity I, whose fibers are the stable and unstable manifolds. So, regarding linearization problem, back to 1981, Marco proved that the pair of transversal evolutions on the plane with a hyperbolic composition is linearizable. And in 2013, we get this result for normally hyperbolic composition. So let me just come back. This result gives the whole set of normally hyperbolic compositions. This gives a lot of results about the case of a hyperbolic composition. So this can actually be characterized from that. So if phi1 and phi2 are linear with a hyperbolic normally composition, then the composition is actually hyperbolic if and only if n is even the dimension of the whole space. The evolutions are transversal, and the common dimension of the fixed point subspaces is n over 2. This number 2 generalizes it for nonlinear evolutions. And 3, about normal forms. I didn't bring the normal forms, the algebraic form of these germs, and I'm going to not go into many detail, but I think it's worth mentioning that the classification of pairs with the hyperbolic composition can be simplified because it involves only classification of invertible matrices of order R, where R is precisely the dimension of the common dimension of the fixed point subspaces are more generally the submanifolds. This is a result for in general, not necessarily for linear pairs. So geometric information on dynamics. This is something that in collaboration with Isabel Laboriot from Porto and Patrícia Vasfelli from Universidade Estadual de Maringá. And so what about the number of symmetries in reversible discrete dynamics? When I say symmetries here, I'm saying in general symmetries or reversions. And so are they infinite? Is this number infinite? Why am I asking that? So we ask that as soon as we look at the definition of a reversible map is. So F is a reversible map, a phi1 reversible map if we F composed to the left with V1 is also revolution, F is the composition of these two, and F is V2 reversible. So, as probably all of you here know that this is another evolution that appears very naturally from this equality, and we have many others. So we have actually an infinite symmetry. So if Phi1 is an evolution and F is a diffeomorphism, which is Phi1 reversible, and such that there is no iterate giving identity, which is, this is just saying that my dynamics is not trivial, then F has an infinite number of symmetries and an infinite set of reversing symmetries. The visible, the apparent, obvious reversing symmetries have these two patterns for any k greater than 1. So Phi2 is one of those in these classes and Phi1 is in here. But these, this grid set is not all that we have. Actually, there are examples that are very simple linear examples that show that the group of symmetries in this discrete case can be a Lie group of positive dimension. Okay, so one thing that we can have as a consequence is chains of fixed point sets. So in this setting, if we have these two chains, and this is a chain in the sense that if we iterate F, we jump from one set to the other. And this holds for the two chains. So here we have this pattern. You see, we have the important ones, say the generators of my discrete reversible TVO, Phi1 and Phi2, and we have the evolutions with the primes from left to right, with increasing indices, and if you look backwards, we have increasing indices with Phi without the prime. And this goes in a similar way for the odd indices. And as an immediate consequence of this is all fixed point submanifolds of involutions with odd indices, they have all the same dimension, which is the dimension of fixed of Phi1. They are all here. And number 2, all fixed points of manifolds of the evolutions with even index have dimension all equal to fix of Phi2. Illustration. A linear diffeomorphism which is reversible under Phi1 and Phi2 plane, and these straight lines are the fixed point sets. So it follows from that chain that if we start, for example, on the fixed points space of Phi2, so on this line, we should jump to fix of Phi2 prime, and then to this one, and then to the other one, and then we go from one straight line to the other. Well, one question that we asked was, what happens in between these lines? So, if we start in a connected component, say in this unlimited triangle, if we start from here and we iterate boundary are the fixed point sets of two neighbors in the chain. So that's what we see here. We have this pattern of reproducing the dynamics through the components respecting that chain. So this is actually a general result. That's what we call the alternation of connected components, which is the following. So if phi1, this is actually my last slide. So if phi1 and phi2 are two informations, not linear, but we assume that the dimension of the fixed point submanifolds is n minus 1, then F, the composition, interchanges the connected components of the whole space when we extract the union of the fixed point submanifolds. Right. So just to get a rough idea of the proof of this is the first and the easy part is the cases where we have the situation as we see in this picture, when the boundaries are precisely these fixed point subspaces. But there are cases that the boundary is just the accumulation point of elements in the boundaries converging to a fixed point subspace. And they can have part of the fixed point manifolds. So this was a tricky thing, but the main idea is let's have the chain as the basis for getting this result. So this is basically what we have. And I think that's it. I'd like just to mention that I have a student now. He's an undergraduate student, and he's working with three evolutions. What he finds is that not only the trace of the two evolution is an invariant, but also the trace of the composition of 2 by 2, and also the composition of the three evolutions. So he's doing a very nice exercise of linear algebra with that, because when we compose three evolutions and we are interested in the non-abelian case, because the abelian case is very simple, if we compose, we explore the properties of the trace of three matrices, and these do not, if they commute cyclically, then the trace is an invariant, and in the end, the trace of these three possibilities are invariant, and they generically are also complete invariants. So finally, the list of references.
Questions? So let's take the speaker again. We have some minutes until the last one.
First met Marco at this meeting in 2008, if I remember right. You can see a few familiar faces. The next time I met Marco, I believe was in Barcelona. And he must have spotted that I was a bit of a naive kid who hadn't travelled very much, hadn't spent time immersed in other cultures, couldn't speak the language, still cannot speak any language other than English. Unfortunately, I wish I could. And even though Barcelona wasn't his hometown, he took me around everything. He showed me how to work the metro, how to work the buses. He showed me where to get my groceries. He took me to nice places to go to for lunch and for dinner. And I still have written some of my best theorems in one of the places, in the sandwich shop in Lidia, where we used to go, all written on napkins and stored very carefully before they go into papers. Marco's an amazing human, besides being a wonderful mathematician. And back in Bristol, when I started in non-smooth dynamics, two different colleagues introduced me to two different papers, and they were both by Marco and Teixeira. One was on singularities of vector fields. It's a paper that actually inspired a lot of the ideas in here, which will not have anything to do with non-smooth dynamics, but can be applied to that equally well. And the other paper was on what we came to call the Teixeira singularity. So it's an honour to be here celebrating with Marco and all of the ideas and people he's brought out into the mathematics community over the years. As I said, I'm not going to talk about non-smooth dynamics today, which is what people who know my work mainly know me for. Recently, something interesting in catastrophe theory has fallen into my lap. Applying catastrophe theory to problems where it's not supposed to be applied. This is kind of something I like to do, breaking the rules of mathematics rather than doing things nice and rigorously, and then letting clever people like my friends from Barcelona and Brazil do all of the clever, rigorous stuff later, which is very much what I've done. So a lot of you work in bifurcations and singularities, but I wonder how many of you have heard of René Thom and catastrophes? About half and half. So René Thom, when he came along with this idea of catastrophes in the 1950s, there are some characters here who were around in those early days, so be careful what I say. But as I understand it, it was a very revolutionary idea. He gave us this idea that if you know the number of dimensions in a system, and you know the number of parameters, then you know the kind of bifurcations and stability changes that can happen in that system. And they take a very strict set. It isn't just that anything can happen. Now, that was all very good. These are the elementary catastrophes. Some of these names are things you recognise even if you haven't heard of catastrophes. Folds, cusps, maybe less so, swallowtails and butterflies, which are things that require more parameters. Have you heard of catastrophes of vector fields? Some people informally use the term vector fields, but you're not supposed to. Catastrophes are supposed to apply to potential systems, gradient systems, gradient vector fields, but nothing outside that area. But that's what I want to do. I want to apply catastrophes to everything. Now you have to be careful if you apply catastrophes to everything, because catastrophe theory also fell into a lot of disrepute in its early days, because that's what people did. They were so excited about the idea, because some people were, like Thom and Zeeman, that they applied it to everything. So you go looking for cusps, and you'll find you can explain everything in the world with cusps. You can explain whether people will buy or sell your product. You can explain whether a crowd's going to panic. You can explain whether a building's going to catch fire. There's still a few of you young enough here to fall in love. You can explain whether or not your relationship is going in love or hate using catastrophes. Always just a cusp surface. Look, always everyone uses the same surface. These are genuinely all from research papers. So in the early days they went a bit crazy. And of course a lot of this is far too airy-fairy to really explain it. So I'm not going down that road. Catastrophes started to disappear a bit as we wanted to study vector fields and dynamics. And really what we talk about these days is singularities and bifurcations. So for instance in vector fields and ODEs, you'll be familiar with, instead of folds, perhaps nodes, cusp bifurcations, and then interest went into other things, well, oscillations, Hopf bifurcations, Tarpin's bifurcations, and all sorts of other things. In the textbooks, for vector fields, these become harder and harder things to study, and you'll find a limited number of cases of these that are really described. But they are still just the start of a massive hierarchy of what must be loads more bifurcations. And what if you're not just working in ODEs? What if you want to study partial differential equations, or stochastic differential equations, or averaging theory? And that's kind of the problem that landed in my lap recently. As I said, catastrophe theory already should only be applied to potential functions, and certainly none of the things on this list. But I was given this problem recently by some colleagues in Bristol who were studying a biological reaction diffusion equation. Don't worry if those words don't mean anything to you. Don't worry if this diagram doesn't mean anything to you. Essentially, this is a bifurcation diagram. So these are two parameters of partial differential equation. Actually, here's the thing, it's a bit of a beast. It's a four-dimensional partial differential equation, so it's got time derivatives, spatial derivatives, diffusion terms. Two functions here, both of which are cubic. This system can have up to 9 steady states. These graphs here show what the people studying this are really interested in, which are global wave states. They're basically heteroclinic connections between one steady state of the system and another. That's what these things show. Some potential in this biological system going between one steady state and another. But underneath all that are the steady states. If there's no steady states, then you can't connect steady states using heteroclinics. You can't have wave states. So underneath all of this is the steady states of this system, which are basically where these F's sit. In any of these, where this function is 0 gives us the steady states. That's what we're really interested in. That's the most simple. So in this bifurcation diagram here, these black lines are fault lines. So they're just places where Saturn no lines. They're places where, as I cross a black line, two steady states will annihilate and become 0. So, what my two colleagues, Fahad and Alan, noticed was that there's a bit more than just fault lines in here, and that computer can identify. What it could identify was, you can see that along some of these fault lines they form a classic cusp shape. Along this one forms the classic cusp. But if you put all of these faults and these cusps together, they look like they're forming something higher. And they thought it looked kind of like these catastrophe sources. They look kind of like these swallowtail shapes, is what they thought. But this is a partial differential equation. Catastrophes do not occur in vector fields if they're not gradient systems, let alone partial differential equations. So why are these things turning up here, and are they really turning up? Is the question. You go looking in the textbooks, as I had to do, and you will find no mention of swallowtails or butterflies or vector fields, certainly not for partial differential equations. You won't find the conditions to work out whether anything higher than a fault cusp is going on. Explicit conditions. So I needed some explicit conditions, and I just went looking, and we stumbled upon something rather interesting. So as I said, these catastrophes should not turn up in equations like this. They should only turn up in simple potential type functions, where my f is some gradient of the potential. And these things are simple polynomial equations that we can write. And yet, well, again, how many of you are familiar with these catastrophes? All of you who aren't on it, you actually are very familiar with all of these catastrophes. If you've ever had a coffee or a beer out in the sun and sat there and noticed one of these cusp shapes on the surface of your drink, or if you've looked through the stem of your wine glass, reflecting onto the table, and seen these light patterns, you're looking at quite high order catastrophes. These are also ones captured deliberately by my former PhD supervisor back in the 80s. This is a very, very good swallowtail catastrophe caught in light reflected through a thin film. You'll see these, those of you wearing glasses, you might see the droplets of water collect on your glasses or on your windscreen. And this is a very useful butterfly captured again in light through a thin film. Every time you look at a swimming pool in this country, I imagine in the summer you must do an awful lot of swimming. Next time you're looking at a swimming pool and you notice the rippling lights on the surface, run to the university and tell your boss you need to charge your time to your grant because you've been doing very high dimensional bifurcation theory. Let's see if this will work. So when you're looking at the ripples on a swimming pool, what you're looking at are sections through these bifurcation surfaces. Actually something even more complicated called umbilic bifurcation surfaces that I mentioned. You're taking sections through a 5 or 6 dimensional space, a parameter space of these catastrophes, and you're seeing it all unfold as the water ripples change the parameters of the system. So you're very, very familiar with these things. So it wasn't that surprising when shapes like that showed up here that I kind of recognised them. But are they that? And how do we justify being these catastrophes and shifts? Is there a correct way to do bifurcation theory for vector fields? At least one of these. So, if you think you've got some kind of bifurcation in a dynamical problem, a vector field, or a PD or something else, how should you go about doing it? For catastrophes, as I say, something of this form, you've got very simple conditions, because they just take these simple polynomial forms, and all you have to do is check some number of derivatives of x. And it's the number of derivatives of the parameters of this. For a fold, you just have to check one derivative, which is plus or two parameters. It just goes up one at a time. For a vector field, we have lots of stuff there, lots of amazing, very detailed work that tells us the normal forms of certain bifurcations. The topological classes that they sit in, the germs of them, but they have lots of topological global conditions involving stability, connections, clinics and heteroclinics, limit cycles, not very explicit things that you can just sit down and calculate where is this bifurcation or what bifurcation is happening in this system. Only really explicit algorithm I could find for working out what kind of singularity might have is something called the Boardman classification, which I'd never heard of, and I have to thank a colleague of mine, David Chillingworth, for putting me onto this. I'll show it very briefly, too briefly to really make sense, but I think some people should be aware of what's out there. So Tom had these ideas in the 50s, and as far as I can tell, people for the next 2 decades tried to work out, one, were his ideas rigorous, and were they even correct? And one of the ways they came up with was this Boardman classification to algorithmatize his classes of catastrophes. And here's roughly the idea. It's simple in its premise. I take my vector, my function f, my multivariable function f, the list of variables. I'm going to call them the first Boardman symbol, which is this. It's just a list of the components of f, and then the determinants of its Jacobian. I should be slightly more general. Instead of just the determinants of the Jacobian, I can take all of the minors, the submatrices of the Jacobian, and determinants, and put all of those in a slightly higher order. Then I'm going to take all of that, and I'm going to dump it into another sequence, and then take all of the submatrices of the Jacobian of that, take their determinants, and put all of them in the list, along with everything else I had before. And then do the same again. Take all of that, put it in, take its derivative, and find all of the minors and submatrices of those, and their determinants, and list all of them. And on and on and on and on. And when you've done all of that, and form this rank list of all these symbols, you go back and look at the co-rank of all those matrices, how degenerate they were. That tells you what singularity you have, and exactly what type it is from all of that germs. It's a wonderful and very, very general idea. And so that gives you the Boardman symbol, which is basically a list of the co-ranks of each of those symbols. A couple of problems. How many calculations is that? If you were watching closely, that involved nested products of binomial coefficients summed over all previous binomial coefficients for each step of that algorithm. You can't work that out in your head. I worked it out again recently, but this is how many calculations there are. We don't see these kind of numbers very often in bifurcation theory or singularity theory. These are more like cosmological numbers. My problem had 4 dimensions and at least 5 parameters. And so to look for a singularity using this method, I've had to do 3 times 10 to the 30 calculations. Well, I don't think about this. It's got a whole lot of problems and nothing for Marco's students. So over Marco's lifetime so far, doing 1 calculation per second, you can still need 10 to the 18 students to get this done. So his students beware, if certainly more staff looking in. That's a lot of students even. That shouldn't be how it is, that's ridiculous. And of course a lot of those calculations turn out to be redundant, zero. The other problem is, this only works for mappings. It doesn't work for vector fields or any of these other things I want to apply it to. And it was well known from early on, and Homer especially pointed out, that it doesn't distinguish between some bifurcations. It's not perfect as a method, but it was used as one way to critique Tom's methods. What we should have is just, if we have n dimensions and r codimensions, r parameters, just the number of conditions that tells us, the number of equations to solve. exact coordinates of which it happens, exact parameters of which it happens. So we should have that plus that number of equations and so on. And that's what catastrophe theory actually gives us. And that's what I'm going to show you. And it works for vector fields and anything else you talk about. So these are just the conditions. I call them the B conditions, or the BG conditions, the bifurcation conditions, and the genericity conditions. The B's, the generalization of those simple derivatives of catastrophe. They're just a bunch of simple determinants. As far as I can tell, these things haven't really turned up in bifurcation theory or singularity theory. They are in a way an extraction from Tom's method. So basically this B1 is just the determinant of the vector. I take B1, I then drop it into one of the components there, and that forms my B2 symbol. I take the B2 and I drop that in again, and I'll get a B3 symbol. I nest these through and I get a set of B conditions that I can consider. And if I have a codimension R, singularity, catastrophe, then R of these should vanish. You never get anything for free. All of that other muck of Tom goes into some non-degeneracy conditions. These are a large set of calculations, but they're just small. You just have to calculate them to make sure they don't vanish, to make sure this thing's general. Just to give you an example of what these things are, there's a nice sort of normal form that you can put these in, the principal form. Arnold called this these are principal families. In this form, these B's reduce exactly to just the X derivatives, generalizing those from catastrophe theory, and that form just has the actual catastrophe forms in the first dimension, simple things like those. So, this at first allows me to go back and solve that partial differential equation that I was dealing with before. So this was it. These are my two, my F and G. I keep switching between big F's and little F's here. They were both cubic, so this thing can have, as I said, up to 9 steady states. And according to those Tom Boardman conditions, this should have taken 10 to the 30 calculations to work out. So this really was the back of an envelope calculation in the end, or rather the back of a napkin, and rather than talking. And I did this over lunch somewhere in a nice little cafe. So solving the folds, I don't want to really look at these conditions. This is just to show you that this really becomes a simple by-hand calculation. For this 9-point system, you can find the cusp. It turned out the thing they were seeing, they suspected they were seeing, was not a swallowtail, but was one higher, it was a butterfly. And there's even higher. There's up to codimension 6, the star singularity. Beyond the swallowtail and the butterfly comes the wigwam and the star, and they started having great fun doing it. So clearly solved that problem, and from that pattern I showed you earlier, this thing breaks down to a butterfly singularity. Okay, good, all very well. In the process, you get access to just play around a lot with vector fields and looking at their catastrophes now in ways that you did before. You can have your simple folds. You have this whole class of other folds, which Freddie made quite wince when I started talking about this, but this now in this language is just a fold singularity with some interesting stability properties. This was a class of folds opened by Mortier, String, and Sotomayor. As a whole, this is the beginning of a whole family of fold bifurcations, nil-Bolton singularities. And you can play around. I just had some fun once I started doing this. I created a fold whose fold set is a Whitney umbrella, just for fun of it. A novel cusp that I'd seen before and had an interesting fold surface. And seeing a swallowtail for, I think, the first time in a bit, really see that swallowtail shape. You can play around and come up with some interesting bifurcations and singularities. There are important ones in that though, and one that genuinely I don't think has ever been seen before in vector fields, which is slightly strange. And if anyone can correct me on this, I will be very, very happy if you can. So take a system with 4 equilibria. What kind of bifurcations can that go through as it changes? In terms of just the equilibrium. So it can go through a swallowtail. We don't really talk about swallowtails in vector fields, but they're certainly just a general extension of cusps and so on. And the general forms for these appear in a table in Arnold's book, for example. So you can certainly have a swallowtail, and that's just detected in this one by these conditions. Then you can have another kind of catastrophe, for which the B condition is this thing. I won't go into this too much, but this is something called an umbilic. And I don't think umbilics have ever been talked about in vector fields. surprising. They're extremely important in attention systems, in gradient systems, and in catastrophe theory, and in particular its applications to physics early on through the 70s and 80s. Those light ripples I showed you on the surface of the pond, those are umbilicus. Both of these involve just more equilibrium. So this is the singularity in both cases. Its topology looks slightly different. There's not much to look at here. The red line here, these are two null points, so where f equals 0 and g equals 0. So the blue line is where f equals 0, and the red line is where g equals 0, just to help the visualization. But they look a little different. As you perturb them, they can fall 0, equilibria, 2 equilibria, 4 equilibria, but the form, for those of you squinting, make it a bit bigger, the form of those equilibria is a bit different. It's fundamentally different. In this case, I have 2 saddles and 2 nodes, and the nodes have the same stability. In this case, I have 2 saddles and 2 nodes, and the nodes have opposite stability. There's also an elliptic curve, where you have 1 node and 3 saddles, or 3 nodes and 1 saddle. And this actually is codimension 3, while this is codimension 4. In gradient systems, the umbilic is codimension 3. In a general vector field, it appears as codimension 4. And then besides singularities, then we can go and apply this in other places. And this is where I think it's going to start to be really exciting. Tom, when he did this work, was working on genesis, as it seems a lot of people were at the time, the growth of living systems, the growth of living beings, cells, how cells change and form structure. That was the idea behind trying to come up with this catastrophe. Someone else working on that about that time was Alan Turing. And he had a very different idea. He was doing something quite different. He came up with the idea that in a diffusion equation like this, if you had stable steady states, they could be destabilized by these diffusion terms in something like a hot bifurcation. A hot bifurcation now not in a simple vector space, but out in the diffusive space. And that would take simple steady states to create these sort of patterns. So if you see anything about pattern formation, you may have seen this kind of thing. Through Turing's bifurcation, diffusion-driven instability, this is supposed to give us kind of activity that we see on animals, tiger stripes, and how plants delineate certain structures. But Turing dealt in his paper just with linear vectors, linear functions. And he said at the end of the paper that he thought if you made those things non-linear, then you'd be able to see not just how patterns form in the first place, but how they progress from one pattern to another. So how animals not just grow and form one pattern, but change pattern through their lifetime, through some kind of bifurcation. And little did he know that across the channel in France, René Thom was creating just the kind of the ideas that you needed to describe that progression by catastrophes. And as far as I know, those 2 ideas have never been put in, because you can't apply catastrophes to these kind of systems. Except you can, if you don't care about the rules of mathematics, you just go talking about catastrophes and vector fields. So these ideas seem to allow us to bring these things together. And these are patterns changing here near a cusp of catastrophe, and here near a cusp of catastrophe. There's lots of work still to be done to understand this, but I think it's an interesting area that we can start with. This seems to open things up. So if I have time, because we're all quite geometrical people here, I wanted to give you actually some intuition into what these being conditions are doing, because it's very simple. So at the moment they're just a bunch of determinants. But this was really the back of the envelope idea I had when I came up with these. If I take, so let's take a vector field with 2 components, F1 and F2, and I'll draw their null points. So where F1 equals 0 and F2 equals 0 in space. That's where I find an equilibrium of the system. It's the equilibrium of interest. And if I perturb that, that's obviously those things intersect transversely, so perturbing them, things like this. Now that requires that the determinant of F1 and F2 is, there's certainly some place in space, some permanent space where it's 0, but then I better not go through here, because otherwise that would be telling me that 0, that those 2 are not transversal. So this must be non-zero, and then that's just a simple equilibrium. These ideas I really started from one of those 1993 singularities of vectors. I think if you go back and read that, you'll see the echo of what I'm doing. So if that's violated, if this B1 equals 0, this determinant equals 0 condition does pass through, what that tells me is my null points aren't transverse, so they must be tangent to each other. So if I perturb those, I'll get that 0 or 2 equilibrium. That requires that B1 is transverse to F1 and F2. So that gives me some B2 condition. That must, it's going to be 0 somewhere, but it better not be 0 from there. And then that gives me a follow. And then you just carry on. If that condition is violated, and B2 is 0 at my point of interest, that tells me B1 must have been actually tangent to my other null points there. And then actually my null points would be cubically have cubic contact. And then when I perturb that system, I'll have either 1 or 3, provided that B2 is transverse to the others, and so on and so on and so on. So that's all these conditions are doing. It's a very nice bit of geometry. So then I have plus, and I carry on from there. And that will just give you a whole hierarchy then you can build up and just apply all these ideas simply to a vector field or absolute field. So that's why it works. The rigor of why it works, what I'm really doing in those arguments is A, concept equivalence, which is an equivalence that just preserves zeros. It doesn't care about all the properties of a vector field you should care about. And if you are rigorous at all, you should be very worried for the day. You completely ignore the stability, completely ignore directionality of the vector field. There's all sorts of stuff just and again, I should thank David Chillingworth for introducing me to this idea of K equivalence and concept equivalence, and that was really what I was preserving here. I was kind of relating back to that top order classification. So that would be all very well. There are some, I'm not the kind of person who shows proofs and theorems much in my talks. There are some proofs and theorems showing that in terms of at least this stuff relates back to the top order classification. The proofs that all of this is preserved, contact equivalence, are to be forthcoming soon. So essentially this K equivalence is what gives us the ability to describe the catastrophes of vector fields. Now, because we're not doing strict catastrophe theory, I call these underlying catastrophes. They underlie all of the other structure that's going on in a vector field or a partial differential equation that we should care about. But we get all of the catastrophes, much as they are, they take only the minimal number of functions to define them, so just the number of variables and parameters that you have. And so you can explicitly define these catastrophes. In doing so, they preserve the number of equilibria you have in your system and the manner in which they are. And they ignore, of course, stability, cycles, homogenetics, heterogenetics, all that really important stuff. If you want to preserve all that stuff, then you have to go to, at least the textbooks will tell you, to topological properties. You have to look at the solutions of the problem and actually see where they're going. And only then do you find the full topological motivation analysis. The trouble is to find those, to solve, to find out what kind of singularity, what kind of bifurcation class you have. You either have to do a normal form reduction or a center manifold reduction. Solve some unknown number, typically, of topological conditions, which is tough. But they do preserve all of the properties and orbital topology and stability of the system. They don't preserve eigenvalues. We know that foci are topologically equivalent to nodes. But we don't really care about that in this type of applications. If you want to preserve that, you have to go all the way to smooth equivalence. But that's just coordinate transformations. That's not interesting. The surprise to me was that there's a massive world in the middle between those, and this is going to be the really exciting stuff that's yet to come. It turns out we can really fill that gap between this contact equivalence, these underlying catastrophes, and the topological modifications. So the work kind of started on this through the 70s and 80s, and we are still working to understand a lot of the work that Mortier and Sotomayor and Rousseau did on this. Essentially, with contact records, we've taken a Taylor expansion of a vector field and just looked at the 0 forward to if you expand the thing to its to its kj, there are a whole bunch of invariants in there, starting with the trace and determinant in the first one, but then a whole load of other invariants that you can find that have to be preserved in order to capture. And it turns out they can capture, as far as we can tell at the moment, all of the stability properties. I didn't think at first this was possible, to capture all of the stability that's going on locally in the bifurcation. I thought you really did have to go to topology to do that. And I was told very clearly by a very senior colleague that all of this was really the wrong way to go. You couldn't do this at all. I shouldn't do this. It had to be done topologically. It seems that's not quite true. And the work on this once it began in the 70s and 80s. You can capture so much of this just from these cages. So essentially you have to find enough terms that can span, that can capture all of the geometrical invariants of the kj's or whatever singularity. And then you will have full catastrophe classification in which you can find these things with just the right number of conditions, a minimal number of conditions, that still preserves stability. That work's all forthcoming. It's work I'm doing with Douglas and with this chap who some of you may recognise, Pedro Herrera, who I've stolen from here. You can't have him back. This is his hostage photo. He's chained to a tape in Bristol. I've learned his visa and his passport. I'm keeping him. He's the guy who's really making all this work really forthcoming. So that's really it. So the simple set of BG conditions for these underlying catastrophes, which give us, as we're learning, these break down into simple correct ones, which are your folds, small terms, butterflies, fairly simple things which turn up in Arnold's classifications, and certainly there in the traditional vector fields. These umbelics which don't seem to have been touched in vector fields at all. And again, this is the one I'd be very happy if someone could correct me on that fact before I keep writing about it. And then there's a whole other class of co-rank ones, but with the center manifold, as I mentioned too. So these are things where you have like folds, but you also have a hot verification going on at the same time. These are called opposing singularities. And so these are what were studied with the breakdown by Mortius and by Street. And we are, let's put it up here, because we are still digging into this area. This is really helping us understand these jets and how you capture the information. And it was done with, in those days, by all kinds of ways of trying to get our heads around, which we think we can simplify and turn into the form of this simple attachment. So, if I know it's not am I allowed to do a couple of minutes on this because I know it's so, since people who do know me mostly know me for non-smooth dynamics, I didn't want to give the impression I've left non-smooth dynamics, but initially I was going to give a talk on non-smooth dynamics, but my work in this area has taken a bit of a different direction. This is going to be one slide. I'm not going to show any mathematics, so I'll give you a flavour of the applications. So, a couple of years ago, a few years ago, we called this the Just paper with Jeffrey Lukin, Zeeman, and Teixeira, which we call into higher dimensions of non-smooth dynamical systems. I'm interested in what happens when we go into higher dimensions, what happens when we go into multiple switches, as has Teixeira been for a very long time, as has Lukin been, going on about certain indeterminacies that seem to happen when you try to apply Philippometric in higher dimensions as multiple switches. So essentially looking at non-Philippometric behavior that occurs when systems become ill-determined as you go into higher dimensions. And actually, the red herring in a way is the higher dimensions. Systems in one dimension with one switch are already ill-determined. They're just hiding it. So if you take the simplest kind of system, this is sort of a mechanical mock-up of just a simple system where you have a crossing. So I have the vector field pointing to the right, which switches to a different vector field pointing to the right. So in a Filipov system, you're always just going to calculate solutions. Just say this passes from player 1 to player 2. At different speeds. Sewing across. It can have hidden terms, hidden dynamics that you put in that would, as this thing tries cause the thing to stop. In one dimension, that's a bit of a weird situation for one switch. But as you go into multiple switches, it becomes absolutely unavoidable. But it turns out there are some. Well, actually, yes, first example. During COVID, I was doing an awful lot of walking. I had a 3-year-old boy at the time. The only way to survive life was to go outside and walk. And on one of these walks, I happened across exactly this problem. So this is a little weir. I looked up what word that is. So just like a tiny little waterfall. And in this weir, so I've got water flowing from the right to the right, and so I'm already getting trapped in this weir. And an object in there that's got stuck at crossing between two vector fields, both going to the right. So I've got something like a discontinuity surface or a regularization layer in which something's just got trapped. Now you can imagine this river could go on for miles inside. So the scale of this thing is arbitrarily small. So this is hidden dynamics. This is crossing, going wrong as you pass through something. And what we discovered recently is that when you look at and you're very keen here on smoothing these things, on regularizing, doing sort of MAT80 regularization, doing lots of wonderful rigorous mathematics, proving what happens to these things. What I've been looking at is what happens if you take this simple kind of crossing dynamics and put in discretization, or put in noise, put in hysteresis, put in time difference, or any kind of stochastics. And when you do that, and you just look at a simple one-dimensional system, at the transition points of as I move around in this thing, and I maybe jitter around before I manage to pass through, even for tiny amounts of time. The transition surfaces are highly unpredictable even for one-dimensional unswitched systems. Now, most of a system like this, those slight wobbles will happen on a tiny time and disappear. You won't see them across the dynamics. But what we now realise is these transitions are highly closely related to market processes, and we're describing the probabilities of switching across these things using Markov probability transition process. So the work we're doing at the moment is going to, the work coming in this paper, is going to start relating Filipov systems with multiple switches much more closely to Markov processes. That's what I wanted to talk about if I decided to start that position. And here's another example. Let's snooker in this country, so you can play pool. This, if you've ever played it, well actually you have to be quite professional to see this kind of phenomenon. This is this phenomenon of kicks you see professional snooker, professional pool. Now simple mechanics doesn't always play like simple mechanics. Believe me, these guys are not rubbish. And they are doing very good shots here. These balls are not behaving as they should. One simple ball rolling into another, they're not conserving momentum, they're not conserving angular momentum. They are getting kicks, they're jumping in an unpredictable way, in a way the dynamics says they should. And it's because at the moment this thing hits, you've got not one but two discontinuities. You've got the discontinuity of the impact, and you've got a sticking discontinuity of the surface. And the two discontinuities mean you fundamentally got an terms like, and you start seeing these things all over the place as soon as you sound again. You start seeing these things all over the place when you start going to multiple dimensions. So that's the area of interest that we're heading into. This one's really weird. He hits that on the right hand side of the wall. All travels to the right. Go and visit Newton and have a word of think about this, because there's no really good mathematical papers that study this. And maybe we'll get some good students to apply some non-smooth dynamics really well to these concepts. Okay, so just a few pictures from over the years. These ones are from Bristol. It's been wonderful to work with Teixeira and all the people who he's introduced me to over the years, to keep their faces, these pictures. Thank you very much for having me here and listening.
Questions?
Hello. Yes. Oh, Mike, thank you for this nice and enthusiastic talk. But I would like to lower your enthusiasm a little bit if you say that you will try to simplify what Soto, Robert and me did, because that exactly is the way we started. We started by looking at the underlying catastrophes. Because at that time, of course, catastrophes were very in fashion. And what we wanted to do was to generalize the ideas that you had in functions, gradient systems, to general systems. So I want to talk about two things, one of which is the co-dimension, because this is very important. But I want to start by saying your conditions P and G, in fact the conditions that we also used at that time. But the condition P and G are in fact invariant under left-right equivalence. I mean the following, no, they are invariant under left-right, it means the following. You can start by a coordinate change, then do the mapping, and then do a completely different coordinate change. So all your notions are in fact left-right invariant. So your catastrophes are also left-right invariant, because in fact that's the usual notion that were used by Tomb and other people in looking at stability of mappings, normal forms for mappings, and so on, like the Whitney normal form, etc. They always use right-left equivalence. What does this mean? Take, for instance, let's say a weak focus of codimension 3. What is the catastrophic codimension?
Weak focus of codimension 3. So by that you mean...
In the plane, I take just any weak focus of codimension 3. What is the catastrophic in your conditions? What is the catastrophic codimension?
What do you mean by weak focus? So you mean one with the vanishing linear
I
stability?
think we all know what a weak focus is. Let's say if you start unfolding it,
Yeah.
you get a hot bifurcation of codimension 3. So a weak focus of codimension 3, what is the codimension in your theory?
Then these would just be Morse points essentially. These would just be stable.
Yes.
So
what you have is, you have as codimension is 0. No, it's clear because you have a mapping, let's say as a mapping, let us precise, x goes to y and y goes to minus x. That's a diffeomorphism as a mapping. All diffeomorphisms are right-left equivalent to the identity, even to the translation. There is but one model, so that means that codimension 0. So there is a big difference in between the catastrophic codimension, if you can call it the catastrophic codimension, and the dynamic codimension. And the big difference is that when you study catastrophes the way you do, since you use right-left, you have, for many phenomena, you have a very low codimension, of course, because you have an enormous group that you can operate on the mappings. While if you do dynamics, studying diffeomorphisms or vector fields, once you choose a coordinate change, you have to use the same at the beginning and at the start. And that reduces, let's say, it's much harder and will increase the codimension of the phenomena.
Yes.
So that also means that when you find something that is catastrophically of codimension 3, and you have nice examples with even with four zeros, that means that the dynamic codimension is going to be higher, at least 4. Probably in what I saw, 5 or 6 even, I do not know exactly. So the underlying catastrophes is a very good idea, nothing to say, and you can calculate it the way you do. That's, by the way we did it too. You need to know, you need to have this knowledge of underlying catastrophe before you start. But then you have to add all these dynamical things, this dynamical stuff. Please do not avoid it if you do dynamics. So, and like you said, you don't see eigenvalues. I even will say more, because you work with null lines and zeros. When you study mappings, you don't see zeros. What you see are inverse images of points. So you can, for instance, in a diffeomorphism, you know that each point has one inverse. In a fault, Each point has 0, 1, or 2. And if accidentally, at the end, as a point you take to 0, then it gives you 0, 1, or 2 zeros. Okay, so the conclusions are correct, of course, but it's not because the theory immediately permits you to work with null lines, with zeros. It permits you to work with points and inverse images. That's all. And it will permit, as I will show in my talk, you can also work with the kernel of a differential. You cannot work with eigenvalues, okay, you said it correctly, but you can work with the kernel, because the kernel is an intrinsic notion under right-left equivalence. That's what I'm going to do in my talk. So that's the kind of remark I wanted to give. So let us say, very interesting to look at underlying catastrophes, but pay attention not to say, for instance, that we might have missed, I didn't say it, but that we might have missed, let's say, a codimension 3 phenomenon. Yeah, we might not have described a codimension 3 phenomenon in the sense of catastrophes, but which is going to be of a much higher catastrophe codimension. So, yeah, the notion of codimension is something subtle, which is much linked to the kind of group action that you have. So, okay, very nice work, but I wanted to make these remarks.
Okay, thank you. Yeah, those are really important. And they are things I didn't say much about. So, absolutely, the codimension, I mentioned it briefly, but I didn't go into it much. And certainly these things only give a minimum codimension for anything. And the codimension that I talked about there, I should be more careful, was just the codimension of the underlying catastrophe. And also, that does make it, I'm not in any way saying it's surprising. I did say that. It's surprising the way that these umbilicals weren't talked about, and I do expect they may have been talked about or written about somewhere, possibly using a different name that I haven't seen, which is why I want to put it out there in case someone can tell me where it appears. It isn't surprising they weren't classified in this way, because as you say, the actual codimension of them is going to be something much higher. If I've got those 4 equilibria and I've got now 4 nodes, in a swallowtail they're really easy, they're in a line essentially, they can't have connections. When they're in an umbilic, they're in a square. And now they can have all kinds of connections. So now you really do have to do the topology. So the actual codimension, the dynamic codimension, the topological codimension, is going to be much higher. So absolutely you're correct. All of those things have to be developed. I didn't think they could be at all. And what I advocated in my initial papers was that this was just a tool, a method, to find at least the catastrophe, the singularity. And then it wouldn't tell you the type, it wouldn't tell you the topological type problem. But if you could locate it, it would then enable you to then do a proper local unfolding and find the topology, find the proper expansion, and find the codimension eventually. It was then surprising to me the work that we've been doing with Pedro recently, that you can recover so much of that if you are careful to go back to the K equivalents. So I'm putting away the BG conditions there. They're just a tool to locate these things. Put those aside. You carefully find these things using just K equivalents, and then you build up from there, developing the jets exactly as you did. It does seem that we can capture much of those things. Even for, as you say, the weak fold, there are cases there we haven't fully studied yet, but we are looking at how you capture those stability criteria in jets, and working through it, and we're able to show that we can recover your ill-potent situations and the umbilics and certain things. It's still work in progress, but I'll be happy to talk about that too. But yeah, there's lots there. I should be more careful when I say that. It will be carefully stated in the papers. The other side of it is, I'm excited just to bring all this stuff out for anyone seems to is less familiar with these notions, whether it's the catastrophe theory, whether it's the bifurcation theory that you guys did, some of these novel examples of bifurcations. We're hoping to write a paper where we're just going to revisit a lot of that history and make it, overview it, survey it for younger people and make sure that it's all still very much there in the current education that we're on, because there's so many profound ideas there that we are still just going to look at.
Someone else? So,
Nice talk, Mike. First, please give Pedro back to us because he has a thesis to defend. My first question is the PG conditions that you have derived, they are equivalent to the Boardman symbol condition?
Yes, so essentially they're a subset of them. So when you actually look at the Boardman conditions, this is proven I think in the 7th paper, you find a whole load of them are actually zero, a whole load of them are equivalent, or you just get rid of them. And under certain conditions, they collapse down to just this precise number. So I call them more carefully full underlying catastrophes. The full condition gives you everything you need to reduce it down to that. So there are caveats in there. It's all in the book.
Okay, and the BG condition is for vector fields.
Yes.
But you have also showed some partial differential equation.
So in the partial differential equation, so in a vector field, you're just looking at zeros, so you're just setting the d by dt to 0. In a PDE, the first thing you look at are the homogeneous steady states. So that just means set everything to 0 as well. You can turn off the d by dx squared, you turn off the d by dt, you're just left with that field 0. So that's the simplest. So it's a simple thing. The point is that because they only respect the 0, they don't care about the dynamic properties. They can apply them whatever system they're in.
Okay, and well, it's not the last one, but when you say underlying catastrophe for vector fields, you're basically talking about equilibria, right? The surface that equilibria. Can we talk about underlying catastrophe for higher dimensional invariant sets? For instance, limit cycles and etc. I know I'm not talking about the conditions. It would be
Sure.
much difficult.
I don't know. That'd be an interesting area to go into. So you can certainly, it seems, deriving from maps, so for instance from Bokhari map,
Yes.
you can use that to describe limit cycles. That's in progress again with Pedro. But for other invariant sets, I don't know. That would be an interesting area to look into as well.
Okay. And the last thing is about your last part of the talk, the non-smooth. I think we have some in Markov process, statistical. I think that we have some people here interested in this topic that we can. I can introduce to. Thank you very much, Mike.
Someone else?
I would like to know if the trace of that B matrices have some value, if the trace of that matrix, if it's 0 or not 0, if it provides information for you. Because from the dynamic point of view, if the nuclines are transversal and the trace are also not 0, then it's hyperbolic. If the trace is 0, then you have a center focus problem. If that first B1 is 0, then at least one eigenvalue will be 0. And the trace will tell us if the other eigenvalue is also 0 or not. So from the dynamic point of view, the trace has value, has information. And for this underlying catastrophe, it also provides information.
That's pretty safe, no. So it was my hope when I first wrote them down, either from the trace of the B's or the G's, those G functions, because they capture everything else that's going on, and the derivatives with respect to the parameters, that they would provide some of that dynamical information that I've ignored. No is the clear answer. So you have to, and I left that behind, so very much the BG conditions are really just a way to find the place where equilibria smash into each other. That's just a catastrophe, it's just that dumb. And to do anything dynamically, you have to then find that point and then be a lot more careful. But what we can do, it seems, is do that, but via developing the jets and taking those trace determinant and then how they interact with higher order terms as invariants of the jet and starting to develop those. We will, as we do that, we'll do it in conversation with Freddie and we'll bring him in to make sure that we're...
The trace cannot play a role. Since if you take, for instance, the identity, okay, trace is 2. If you take the rotation in the sense 0, minus 1, minus y, x 0, trace is 0. but they both lead to the same calculations. Because it's right-left invariant. So if I go from one to the other, it won't play a role. It's right-left invariant. You can see essentially these determinants being equal or not equal to zero. Yes, absolutely no problem.
If you have
And
determinants
it
of
gives
zero,
already nice results, but don't expect to have more. Dynamically, you don't see anything.
well, if you have determinant 0, then the trace then will still play.
Determinant is okay.
Yeah, but if you have the determinant 0, then the trace becomes playable. But the trace alone, yes, it will play a special role. But yeah, we can discuss this.
So let's take this picture.
So now we begin with the second part of this morning, and we begin with the talk of Professor Diego Samuel Rodrigues from the University of Campinas, and he will talk about accessing the pharmacokinetics of magnetic nanoparticles in cirrhosis-associated hepatocarcinogenesis by ordinary differential equation modeling and AC biosusceptometry. I did it correct?
Congratulations.
So thank you very much. Don't worry about the title, it's simple. I will show you. A pointer? Is that a pointer? No, I can use the... Yes, don't worry.
Mike, do you have the point? You know, it's no. I think this is the lot of pointers. Thank you very much.
Okay. Thank you. So this is my second time at this conference. As you can see by the title, it's very, very applied. I work directly with the experimentalists, and it's about cancer, this main thing that I will present to you. But before that, I will show you some applications related to Filipov theory, because I know that this is a topic that you like. Just a few words about the collaborators, Guilherme Soares, Paulo Mancera, and José Miranda from Unesp Botucatu, Aníbal Bezerra, Verônica Gonzalez Lopes from this institute, statistics department, and Mats Strand from Fraunhofer, Sweden. So this is the paper, and over the years I have worked with cancer a lot, and it turns out that dynamical systems, people wrote system dynamics, but dynamical systems have been applied to cancer modeling and many ODs. And over the years, this has a great impact on real treatments and simulation and computational science as well. And to show you some examples, I have to talk a little bit about mathematical modeling. So in mathematical modeling, we have to keep the things simple. So I like to show this figure here, where you have some object, let's say real object, but you turn, at the end, you study something that has essential characteristics, but it's simple, a simple object. And sometimes, and most of the time, this is what we can do. So a professor from this institute has this phrase here, that a model of a thing is another thing that looks like it. The thing that is essential is that, despite of the title, we want to keep the things very, very simple as possible. So we want to think about models. So let me show you some examples. So we can talk about the atom, of course, but the topic here is biology. So in biology, a model, it can be an animal, or even cells in a culture, and of course, mathematics. And despite of the simplicity of this simple, very simple, beautiful equation, we can use it, for example, to do some curve fitting in COVID cases. So we have the number of the cases here in Brazil since the beginning, since the first case in 2020. And this is a thing that my first year students did in laboratory physics, because I'm a physicist. And also, not for the whole country, but if we talk just about the São Paulo state, it's the same behavior, but it cannot be that way for a long time, because an exponential growth is very, very fast. So there's a sub-exponential or something like that happening here. And in the beginning of the pandemic, this paper here, the notation is strange, but it's an ODE, I swear. It's the SIR model, so the compartment model, susceptible, infected, and removed. And they added these two authors, the X compartment, that is some infected individuals that are symptomatic. And we use this model to study when you have, for example, a change in the behavior of the health policies, for example. So then we can have some Filipov theory applied to that. And also we can apply the Filipov theory to cancer, as I will show you. So at sometimes when the tumor grows, the population of cell grows, you have to have something extra to do the diffusion of the nutrients, because the consumption of nutrients is proportional to the volume, but the diffusion is proportional to the surface area. So you have to have an extra thing here. But at some examples, we have an exponential growth here. And even using treatment, some treatments, the treatments that I'm showing you are these arrows here. So there are 3 types of treatments. Even in these cases, the growth is still there. but if you combine some treatment, it's not anymore. And sometimes the treatment, the schedule itself, it's responsible to eliminate the tumor. So this growth here, it's interesting in this case that you are applying the drug, and we can think that the more we apply the drug, the better, because we give a higher dose and try to decrease this growth. But we study some dynamics related to that. But the main thing that I want to say is that sometimes if you over-treat it, it's not a good thing. If you think that you have two types of populations, you can use a model of using two ODEs, a system of ODEs to model that. And at the end, as you over-treat it, you end with higher resistant population of cells. So, for one hand, it's good to treat, to decrease the population, but for the other, if you do this beyond some point, you have some population of resistant cells that you really don't want to obtain. So there are some systems that are switched systems that you can use to model that. So if here there are three types of cells in this ODE system. If you treat, you go from a type of cell that is from 1 to 2, and then to 3, the number 3, that is irreversibly a bad type of cell. But if you don't treat, it will grow, but you don't have this resistance. So you want to treat, but not a lot. So this is has been done by Hirata and collaborators, and we studied that also using Filipov theory. This is a part, and another part is that we want to deal with data most of the time. So here I'm showing you a curve where the treatment, where the growth stops in this plateau here, and we want to model that again as simple as possible. Use simplicity here. So we have a bunch of models that we can apply to have some plateau here, some stable state here. A discussion that has been taken in the literature over the years was is there any universal growth law for tumors? And maybe the answer is no, because it's too different, a lot of types of cancer, etc. But we can try to adjust some model, to perform some curve fitting, as I've been showing you here. So this is the part where I work directly with collaborators. These two people are from the School of Pharmacy from this university, and these are cells growing in a plate. But a lot of repetition, so you have also variability, you have to take that into account. And sometimes you don't have as many as observations as you want to have. So you can try to think put some more data, to estimate some data, because the interesting part is the plateau that we want to estimate. So what I did here, beyond the part where I'm showing the confidence intervals and the data, is to use a very, actually the idea is very simple again, because the logistic growth that is this ODE here, it is symmetric. There's a symmetry, again, this point here, if you rotate this curve. So if you have some data that are at that part, you can use that data under the hypothesis that the growth follows this law to estimate some points at the end. So this is what I did in this part. And it turns out there is a conference that is Dynamical Systems Applied to Biology and Natural Sciences that will occur next year in Italy. And I will present this there. So going beyond that, we have also some types of functions where we have a non-monotonic growth, and we can also model that using Filipov theory. So this is a new thing that some of my colleagues that are in the audience are performing the calculations. And also, sometimes we already have also the curve for some model or for some treatment. For example, here is radiation. And you know that the survival curve, a log curve along the dose, it follows this pattern. But this from the 70s. This is known from the 70s, but nobody could explain how we can model that beyond just a pure curve fitting. But ODEs solve the problem and shed light on this phenomenon. And the way that this is done, so we have two components here. One is the alpha, the other is the beta. So these two components for the survival curve are explained using this a model for this system here. So one, these double string breaks that damage the cells, some part of this damage are not recognized, and some part are recognized but not repaired. So these two components explain that, and this was a big achievement to understand how to radiation affects the cells. I had a student from the medical physics that studied that, and to finish that part, let's say the introduction, I just want to show you one more example of simplicity where we can use the cell phone to measure, to estimate some constant, this R constant, or the Boltzmann constant, and we have, this part is constant. P is the variable, so this is an exponential decay. But when you see the data, it's not exponential, it's a straight line. So what's happening here is that the constant of this, the exponent is very, very low. So if you use just a linear approximation of the exponential, you'll be able to achieve that. Okay. In terms of the modeling part of the tumor growth, this complicated title here, we have some magnetic nanoparticle, that what we are seeing over time, and as you have the injection of this nanoparticle, you see this type of curve on the liver, because the liver, takes the nanoparticle. And if you put the sensor at the heart of an animal, you see a decrease, because the nanoparticle goes to the liver. And you can also have a lot of sensors acting together. This is not a simple thing, because you have to take care that one sensor is interfering in another one. But it can be done. And you can also have a magnetic image, not an optical image, but a magnetic image, and also, let's say, some model to explain the measurements. We did that, but it was not so robust, so we continue exploring that. And at that time, those people were studying this sensor in two groups of animals. Here comes the title. And these two groups of animals are a healthy one and another one that has cancer. And they want to know if there's a difference between these two. So we wrote a project and we started working with, again, a simple model. And of course, nothing worked. So we thought that the model was enough, or the measurements were too noisy. But this is simple, but it's too simple. What is missing? What's missing is one more parameter, let's say, to perform the adjustments. So instead of thinking about the quantities at the heart and at the liver, we had to think about the concentrations. So, but if you leave these two parameters, the system is not unique, the answer, the parameters that we want to estimate, and we can see that, we saw that after seeing the analytical solution, but then things were good, and we could estimate not just for one animal, but for all the animals at the same time using this methodology that I will not give you the details, but these are the fittings, and this is the fittings are performed for all animals in each group. We have a mean value for that, for those parameters, and an individual value for each animal as well. So K1, K2, and K3 are the parameters, and K1 has to do with the heart, and K2 and K3 has to do with the liver, and those are different, and the animal has cancer on the liver, so this was basically what was expected. And here we have the root square error in the inter-individual variability as well. So it's basically that. This part is just another thing and related to parameter estimation. And there's a student here that is presenting a poster on that. And yeah, the message here is everything should be made as simple as possible, but not simpler. And yeah, it's that. Thank you.
Questions?
Thank you, Diego. You have showed some Filipov models. Could you talk a little more about the process inducing the discontinuities? The first one is COVID. I think that's the...
Yeah.
when you apply the treatment or not, but there are some others.
Yes, yes.
Just could explore a little bit of that.
So for the COVID, we put some threshold value for the number of infected, where you, if you cross this value, you have another parameters, another value for the parameters. So this is the thing that how the field, the vector field changes. And it's because, let's say, if you have this number of infecteds, you have to put some more effort to do the quarantine and the isolation. K0 is the quarantine, K0 is the isolation, and K is the quarantine. So as long as you have this value, you can put more effort. So for that, model is basically that, and it was studied by us, mainly Thiago, Rony, and Durval, that are the specialists in the field.
More questions? So let's thank the speaker again. Now we have the talk from Professor Regilene de Lazari dos Santos Oliveira from University of São Paulo, and she will talk about topological equivalence at infinity of some planar vector fields and its principal part via Newton polyton.
Thank you so much. Let's organize things here. First of all, I would like to thank the organizer for this opportunity, and I would like to say some words, more than to not forget. I take some notes, so let's go. For me, it's an honor to be here today. As Francisco, I first met Professor Marco Antonio in my defense, and he was a member of my the committee of my PhD thesis. In that occasion, he invited me to do a postdoc fellowship here at UNEC, and I accepted this proposal 2 years late. And I consider that 12 months period of postdoc here was a turning point in my career, academic career, because it was a time of significant learning, during which I participate of many activities, especially the preparation of one of the Brazil-Spain project. It was amazing time. And because of this project, I was able to undertake a scientific visit to Barcelona, and I became definitively integrated into the group of qualitative theory of dynamical systems. I made my PhD thesis in singularity theory. So during that period abroad, I met new collaborators, and I have many opportunities to open my mind and know many new subjects. And everything happens because I was under the abroad umbrella of Marcus Guidance. So from him, I learned the importance of support younger researchers, among many other lessons. So today, I would like to express my heartfelt thanks to him for his generosity, patience, and the support. Marcus, congratulations for your 80th birthday. Thank you for this opportunity. Okay, now let me go further. Let's see if I could control my time, because I know that everyone is hungry, okay? So I chose the subject of my talk because it's actually the first time that I studied the Newton polytopes or Newton polyhedra was with Marco during my postdoc. Okay, so I'm returning to the subject. The first time was here, and now many years ago again I'm using Newton polytopes in my research. So this is a joint work with many colleagues. I will mention them soon. So let's try to fix some notations to understand the ideas. My main idea is not to give you proofs, but I'd like to mention what are the ideas which we use and what are our objective. I think that this is not so unexpected. In fact, it's very expected result. But when we start to work, we cannot find a similar result or a good reference about that. So let's denote by X, the planar vector fields. In fact, the real planar polynomial vector fields. So in this talk, I would like to show you how we could determine the monomials in the expression of this vector field, which, under some non-degeneracy conditions, will give us a topological equivalence between X and this restricted expression, this new vector field, but looking for the singular points near the infinity. Okay, so if I'm saying about the topological equivalence, I must to explain what means equivalence, okay? So hopefully speaking, two vector fields are locally equivalent. If there exists a homeomorphism between neighborhoods of their domains, take solutions from the one vector field to the other. And here I'm not worrying about the time, okay? The time could be or not preserved. This is the difference between local equivalency and conjugacy. For me to prepare this talk was very difficult because I'm always worried about the young researchers. I would like that them could follow me. In the next workshop, I spoke in Portuguese because I would like that they could understand me. Here, I cannot speak in Portuguese, so I'm trying to do my slides for both, okay? For ex-specialists and for young research. So sorry for the ex-specialists. Okay, so if I'm looking for topological equivalence, the idea to find the monomials who will be responsible for the topological equivalence, this idea is not new, okay? For instance, everyone here knows that the Hartmann-Grobman theorem do exactly this, okay? The behavior of a vector field in a domain near of equilibrium of hyperbolic type is qualitatively the same of the behavior of its linearization near of this equilibrium point. And also Brunel and Lineari, showed that there is a topological equivalence between the behavior of the vector field in a neighborhood of the origin and the vector field defined by what he called the principal part, using Newton polytopes, except by the case where the singularity is monodromic. Okay? Here, my main goal is to show that it's possible to establish non-degeneracy conditions under which a vector field, a planar polynomial vector field, is topologically equivalent to its upper principal part, that I will denote in this way, defined by the Newton polytope in a neighborhood of the infinity. This is what I say that it's not a surprise to look for this kind of result. We know that the behavior at infinity depends on the higher terms, but we don't know exactly what are the main monomials, the monomials that are really significant, okay? So in this, we look for several results, we'll research for results in this line, but we cannot find, so we decided to investigate more. So, in other words, I would like to see the singularities the X. I would like to show that the singularities of X and the vector field defined by the Newton polytope at the infinity have the same local behavior. So I could say that this result is like a version of the Brunella-Miali result or Berezovskaya. This is a Russian paper, so I imagine that it's not so famous as the Brunella-Miali because we cannot read it, especially many people could read it as in English, no? Okay, so let's try to understand this is the point, okay? I would like to explain you the ideas to get this result. So what it means to study the behavior at infinity? I think many of you know or heard about the Poincaré compactification. Let me give you a geometric idea. If I have a vector field, a planar vector field or polynomial planar vector fields defined in the plane, put this plane on the north pole of a sphere, and using the central projection, project two copies of this vector field here in the north hemisphere and the south hemisphere. So suppose that here I have a vector field. I took a point here, and the line joined these 2 points, and this line will intersect the sphere in 2 points. So doing this idea, I will project everything here in the north hemisphere, and I have another copy here. This central projection is not defined in the equator, but we could show, it's not difficult to show, that we could extend and analytically this vector field from the plane for all the sphere, okay? Except by the sets v equal to 0, which will represent the infinity, okay? They will be in bijection with the points at infinity. So this is the idea that we apply to study the infinity, but it's really difficult. As we are in a sphere, we could use local charts to write this change of coordinates in local charts. So these are the change of coordinates in each charts. Here, what we call the U1, V1, U2, V2. I didn't write the U3, V3 because they are the same, as in the plane. But when we use the Poincaré compactification, usually we have very degenerate points at infinity. I must say something before. Using this idea, what usually we denote, we draw, is a disk. Okay, that is exactly the projection of this vector field in the north hemisphere in this region, and this is exactly the S1, the equator. So we have here the phase portrait. But when we do that, usually we have very degenerate singular points. This means that points that are not hyperbolic, neither semi-hyperbolic. So there is another way to study this kind of points, which we call the Poincaré-Lyapunov compactification. I'd like to show you a little bit about this. This kind of change of coordinates was motivated by the solutions of this Cauchy problem and this equality. Okay? If you took alpha and beta equal to 1, we are exactly in the case of the polar coordinates. But using these ideas, I will not give you so many details, we could define a generalized Poincaré-Lyapunov compactification, okay? Using cosino and theta. Here, these are the generalized one, okay? They are not the usual one, but they are the solutions from this Cauchy problem. So, again, we have a disk that I denote here, a Poincaré-Lyapunov disk, the alpha beta, exactly as here, okay, but it's in a generalized sense. And again, we could use local charts. So, as in the homogeneous compactification, we deal with directional charts, and the dynamics at infinity can be studied by using local charts. And here I present you some of that expressions in local charts, okay? Look that they are very similar from the previous one. So it's more or less as I have weights, okay, alpha and beta, in the case where alpha and beta are equal to 1, we are exactly in the Poincaré compactification. So, but what is the advantage to use this? Is that I would like to show you in a few minutes, okay? But before that, let's see what happens with this kind of change of coordinates. Again, U and V here have different meanings in each charts, because we are looking for local charts. And V equal to 0, sorry, I erase it here, but V equal to 0 corresponded to the infinity again. Okay? Sorry, no, this is a mistake. Here we are looking for local charts, and the infinity will be exactly the lines, U equal to 0 and V equals to 0 according to alpha and beta. I will return to this point when I apply the changes in my case. Sorry. Then is naturally the question. Okay, I present you a new change of coordinates and how to apply it. What is the advantage? Because why I could see that this is better than the previous one. Okay, so the answer or partial answer for this question comes from the fact that each vector field in the plane, planar polynomial vector field in the plane, can be written as a sum of quasi-homogeneous polynomial vector field in a logarithmic basis. Here it's good to note that I have here some monomials. Here I reserve x and y, and there is a sum which depends on alpha and beta, okay? This part that looks here is what we call the D level of the alpha-beta decomposition. So we are, maybe in singularity, doing like a stratification of the plane by lines, okay? But what is the position of these lines? These positions depend on alpha and beta. Well, if you took this expression 7 and you apply the polar coordinates in the not polar, but the directional coordinates, alpha, beta, we have these two expressions. It's nice to see that using this kind of change of coordinates, we could join in a better way the powers, okay? So here we have the linear part, and here a power that will be really what we want, because we are looking for a special kind of blow-up, okay? So I didn't here I put only the plus. This is what we call the x positive direction, but of course that we have always the x and y negative directions, okay? Will be very similar. And as in the previous case, the case of the Poincaré, in the homogeneous case, we have the expressions of the vector field in these local charts, and the V equal to 0 represents the infinity. Here is, in fact, I will give you better. It's not exactly V, depends on the chart. I will show you in a few minutes. Of course, that is V equal to 0, but sometimes we need to be in the axis. But the more interesting case, that is exactly a generalization, because when alpha is equal to beta equal to 1, we are exactly in the Poincaré compactification. Okay, so now the question, natural question is how to find the good values of alpha and beta? Oh? Because we are stratifying, how do you say this in Portuguese, in English, I don't know, stratifying the plane in lines. So how to find this good alpha and betas? This is the point where we have the Newton polytops. Okay, the answer is that. So if you give me a vector field written as before, okay, this is the quasi-homogeneous form. I'm written a vector field as the sum of quasi-homogeneous form. We have the support of this vector field formed by the pairs M, N, exactly these powers, okay, which it appears in the expression, okay, the vector field. So if at least A, M, N or B, M, N are non-zero, so this power will be in the expression of the vector field, so it will be in the support, okay? And the support will be a finite set because we are working in polynomial vector fields. So now we are ready to define the Newton polytope. The Newton polytope associated to a polynomial vector field in the plane is exactly the convex hull of the support. Let's see this picture. Okay? In this picture, each pi is a point in the support. Of course, that you could have pi's inside of the Newton polytope, no problem. Okay? But the idea is to have the biggest polytope where the points will be on the border or inside, okay? Very hopefully way to say. It's just to take the convex hulls. This is what it means to take the convex hull. And here, each pi is a vertex, and each face, I call the face, but in fact, each compact segment is joined to vertex. Let's copy this picture again. Here, so we have the vertices of the Newton polytope, the boundary of the Newton polytope, and we will define what it will be the lower boundary and the upper bound. Did you remember the title of my talk? I say about the vector field, no, restricted to the upper bound. So let's see what means that. The lower bound will be exactly the convex envelope of the support. So here I represent in blue, okay? So we have the boundary of the Newton polytope formed by the union of the lower bound and the upper bound. So this is what I put here. And of course that the lower bound could be equal to the upper bound when the polytope is empty, okay? The Newton polytope is just a line. The interior is empty. Okay, I think it's the moment to have an example to understand a little bit what I'm saying, okay? So, took this planar vector field, and here I have y3. Since I need to put an x here, this monomial will be associated to this point on the support, okay? -1 that will be here and 3 here. Again, here, if I took 1x from here, I have it to 1. From this, I must put 1i here. So here I will have 3 minus 1. And from this monomial, I have, I will put 1y here. So from this, I have 1, 2. Okay? So this is the idea to write the support using the logarithm basis. Okay, so now if you choose this point in the plane, we have in blue the lower boundary and in green the upper boundary. Okay, just to have an idea how to proceed to find that. So now, did you remember that I asked you what are the good values and how to find them? So I'm going this sense, okay? So now we need to define what is a compactification adapted to the Newton polytope. So the idea is exact to took here. Here is what I must say, okay? We must took the inward normal vectors for each face of the Newton polytope, okay? So if we are in these faces, we'll took these vector fields are only the sense. They are always normal vector fields, but they are inwards, okay? So what is interesting here, if we are in this part, D will be positive, and this part D is negative, where D is exactly the integer where the sum happens. Here we are in the line where the face is contained, okay? So this is the slope of the line. And mu and nu are exactly this normal form, the normal vector fields. So now, consider this collection of the normal vector fields to the Newton polytope, and we need to complete this collection. But to complete this collection, we must do in a very specific way. Here is the collection of the inward normal vector fields. Of course, that you will suppose that they are in the reduced form. And now you add this vector field and this, the first and the last one, if they are not there. You add vector fields always saying, assuming that, or not assuming, but requiring that this equality holds. This is a very, very important condition. And then we also assume, we always must to impose that two consecutive vector fields are not normal to two consecutive segments. So if you have two vector fields in this collection, and they are normal to consecutive phases, necessarily we must include a vector field between them, okay? And more, this is a minimal collection in the sense that there is not another collection such with a smaller number of vector fields than this one. And for our surprise, from the toric geometry, we always could do that, okay? It's not so difficult, this is always possible, and that conditions about the determinant is necessary in order to have each two pairs to be a basis of Z2. Okay, now, using these each two pairs of vector fields, we'll define a map. Here. We'll define a map. Could you see here? I have a sequence alpha and betas, okay? Using them, we could define maps. So look now that we have faces, okay? We have pairs, and we have a map in this neighborhood. So, I must run a little bit, sorry. I will define the compactification adapted to the Newton polytope exactly as the surface, the smooth manifold defined by these pairs, okay? I will join these pairs and use the local maps as local charts. So, in short, let me go for a little more. We have a compactification of X adapted to the Newton polytope using the variety and the pullback defined by the previous local charts, okay? And this happens exactly because we could use the toric geometry. This is defined in the complex case, but also in the real case, M is smooth and compact, and this is a very important condition. Okay, so now each map that I mentioned here will be a diffeomorphism outside from the axis, and the vector field defined by them could be analytically extended to the set. So we have exactly as we have mentioned before in the homogeneous case. Okay, we have a local chart, we have a variety, and you could apply the ideas to got our result. But before that, let's return to the previous example. Here I have the vector fields that are inward normal vectors from the Newton polytope, and before, look that this is the first, this is the end vector field, normal vector. Between these two, I must include one. Between these two, I must include one. This was necessary because the determinant between these two are not equal to one, and so on. Okay, so this is what we call the simple fun. So now, I need just one more definition to state our main result. We will say that given a vector field, the upper principal part of this vector field is exactly the vector field restricted to the upper boundary of the Newton polytope, okay? So I'm restricting to the upper boundary. And now we will say that the upper principal part of this vector field is non-degenerate if when you restrict this vector field to each face Okay, did you remember that the Newton polytopic could have many faces in the upper principal part? When you restrict it to each face, we have no singularities outside the axis. Okay, and this condition is called the non-degeneracy condition exactly because the set of all polynomials vector fields in the plane with a non-degenerate upper principal part is an open and dense set. So now, with one more definition, we could state the main result that I'm saying a lot. We say that a planar vector field is free of characteristic orbits near the infinity if its compactification has no singularities on the boundary of the disk, the Poincaré-Lyapunov disk, with characteristic orbits intercepting the interior of the Poincaré-Lyapunov disk. Now, if you remember the compactification, the usual compactification, we have many singular points and they are, if you don't have singular points, or if you have many singular points and they don't have the characteristic orbits, we cannot glue them. Okay, so here the same happens. We will have many, I could maybe draw something like that. I don't know, maybe in this way. To be able to glue them, I must to have a characteristic orbit. So the vector field cannot be free of the orbit, the characteristic orbits. Okay, okay. Now, if I would like to say that vector fields are equivalent at infinity, what it means to be equivalent at infinity? No, I must to define this. So the idea is the same. If I have this as the infinite, I took a neighborhood of the infinite, okay? And if I have, for instance, two neighborhoods, and I took a point here, there is a solution passing here, there is a homeomorphism taking this point for this, and the solution will be taken for the other solution. The same idea extended to a neighborhood of the infinity as we have in the neighborhood of a point, okay? I'm finishing. And so this is our main result. Given a vector field, a planar polynomial vector field in the plane with a non-degenerate upper principal part, and that is not free of a characteristic orbit near the infinite, suppose that the upper principal part does not have a curve of singularities, then there exists a topological equivalence between the original vector field and the vector field defined by the upper principal part. Okay? See that here is not written modulus focus center because I have this condition not free of the orbit, characteristic orbit. Okay? Of course, that's if the vector field has only one face, we could say a little bit more. To finish, I would like to say that the main point here is that after this kind of compactification, the critical points at infinity will be hyperbolic and semi-hyperbolic. So, in some sense, we are compactifying and blow up in the singularities together, okay, in one step. And this result is published. If you would like to have more details, we could discuss a little bit. And now in this moment, we are looking for some extensions of this result for degenerate cases, and we could show that this kind of family that does not satisfy the non-degenerate conditions always could be, happens the same, okay? The behavior at infinity depends only of the monomials in the upper principal part. Okay, sorry I take some time. Thank you for your attention, and happy birthday.
Questions?
At the beginning, you told us about this alpha-beta compactification, but then you define this toric compactification, where you take all the weights. So what's the alpha-beta? The choice of alpha-beta.
Alpha-beta depends, alpha-beta will be exactly the vector fields. You will have many alpha-betas, no? For each phase, Okay, if you take a face, you have the inward normal vector field that will give you the slope of this face. So the idea is to work in faces. In each face you will have not a face, but in a pair. No, the two pairs, two faces, you have a change of coordinates. So you will apply several blow-ups in faces and glue the things. It's not only one, except in the case you have only one face.
But when you define the logic like this, you use what? Just quantify.
Tá. I cannot give you one alpha and beta, a unique alpha beta. I understood your question. I cannot give you. In fact, it's a sequence. No, in this last work, we could show you that it's not necessary to go up so many times. Okay. In fact, there are only few essential alpha beta, but I cannot give you in this moment the best ones. I have something in mind, but I cannot state yet. But I believe that 2 or 3 phases are relevant. The other ones are not so.
More questions?
If you take the techniques on compactification, the infinity pass to the origin. And if you apply then the result of
Brunella,
coincides with your result?
we tried. That was our first step. You can't. In that moment, the computations, we cannot desingularize the things. I can't explain, but at least in the way that we tried, we can't. That was exactly our first result. We believe that it's just to change and it will be very fast, but you can't. In fact, my point of view is that the toric geometry was the powerful tool to guarantee that you have a compact manifold, that things glue well, and so on. So without these tools, we cannot go further.
More questions? So let's take the speaker again.